Interesting. Well, welcome to another edition of Physics 264 Pre-Lab Tutorials. I'm Dr. Steve Brule. Today we're going to study active filters. We'll learn why filters are important in electronics. We'll analyze a high-pass filter and create a Bode plot for that filter. We'll analyze a low-pass filter and create a Bode plot for that filter. And finally, we'll preview what a bandpass filter would look like for its frequency spectrum. Okay, what are filters used for and why do they work? A filter is a device to remove unwanted frequencies from a signal. Let's say we had these two frequencies coming in our input and they're equal in amplitude, but we want to get rid of frequency 2. We put it through a filter and look what happens to frequency 2. And frequency 1 remains unaffected. So that's what a filter does. It changes the frequency spectrum of our input signal. Okay, let's look at a few applications. An electric guitar uses passive low-pass filters to remove high frequencies in its spectrum. What it does is when you turn that knob, it changes the cutoff frequency for your frequency spectrum coming out of the guitar. So the guitar's signal coming into the pickups goes into the low-pass filter, and then say this knob was at maybe 5, we're looking at a cutoff frequency of around 250 hertz, which means that anything below 250 hertz, or really below here, is unaffected. It starts being affected here. You don't hear it that much though. And then above the cutoff frequency, we see that the frequencies are being attenuated, and the higher the frequency is, the more attenuation we get from what the input was. And by negative 3 dB gain at our cutoff frequency, that means we're getting a attenuation of negative 3 dB. What's negative 3 dB? That's when the output amplitude is 1 over the square root of 2, which is 0.707, times the input amplitude. Okay, so turning that knob, adjust where your cutoff frequency is. If you have your knob at 10, that means that there's no attenuation of any of the frequencies, and your frequency spectrum is flat. So whatever frequencies are being generated by the pickups come out the guitar's output if it's on 10. But if we turn the knob down to 0, then our cutoff frequency is very low, and all frequencies that the guitar is producing are being attenuated. The higher frequencies are attenuated more than the low frequencies, and it creates a very dark tone. And then, as we talked about before, this is like a midpoint on our knob, maybe 4 or 5, so that we're getting a cutoff frequency of around 250 hertz. Well, a stereo system with bass, mid, and treble uses active filters, and what an active filter does, it also has the cutoff frequency and so forth, but now when you turn the knob, it doesn't change the cutoff frequency, it changes the gain of that band of frequencies. So when we turn the knob way up at 10, it's increasing the gain of those frequencies, and you get higher amplitude out for the low frequencies and for all the frequencies, but they're being attenuated down here so they don't sound as loud. And then if we turn our gain down to minus 10 on the dB, that means it's cutting everything in our active low-pass filter down by 10 dB. So the low end is being cut then. Same thing happens for the treble, but that's a high-pass filter, so that allows the high frequencies through, but it's cutting all the lows. And if we turn it up, this goes up. If we turn down, the gain goes down. And then the same thing happens with the bandpass filter, but it's cutting high and low frequencies and just allowing the mid-range frequencies through. When you turn the knob up, it increases the gain of those mid-frequencies. You turn it down, it decreases the gain. Another application of a filter is speakers that we use for our stereo systems. A tweeter only gets the high frequencies, so we use a high-pass filter for it. If we allowed the low frequencies to go into the little tweeter, it would break the tweeter because it's not made to handle those low frequencies. The low frequencies go to the woofer, so we put a low-pass filter for the woofer, and the mid-range speaker gets a bandpass filter. Radio receiver uses filters to get rid of all the frequencies above and below the target frequency that you want to listen to. Power supply conditioner uses a filter. Remember when we used, what was that called? The rectifier circuit. So we came in with an AC signal and we ended up with a rectified signal, but it was bumpy. Well, you can put that through a filter to get rid of the wobble in there. So we want to get, it's a low pass filter, so we get rid of the high frequencies and end up with just a low ripple. And then an oscillator, we're going to look at that next week, but this function generators use filters to create their sine waves and many more applications. Well, let's get into analyzing a high-pass filter. Here's the high-pass filter we're going to use for this lab. And by golden rule number 1, if we put the positive input of our op-amp to ground, then our negative input will have no potential difference between that, and so the negative input is a virtual ground. It's not actually connected to ground, but the op-amp creates a situation where that point is always at the same potential as the ground. Okay, by Ohm's law, the current through R1 and C1 is IN. We use this equation, the voltage over the reactance. And then since these two things are vectors, we have to take the square root of the sum of the squares because they're at 90 degrees from one another. So there we have the magnitude of the current we get. We see if we put in frequency of 0, this term becomes infinity, and this term then goes to 0. So, so for frequency of 0, we get we get no current coming through this high-pass filter. But then if we put in a frequency of infinity in here, this term goes to 0, and we get the output is just Vn over R1. So that's a high-pass filter. We know that the current that's coming in here is going to go through here because there's no current that can go through the input by golden rule number 1. And from Ohm's law, we can say that the voltage drop across the feedback resistor is minus the current through it times the resistance. So there's the current that we got in the previous slides. Solving for V out over V in, so I just divided by V in here, we get this. This is called the transfer function for our filter. And we're only interested in the magnitude of the transfer function, so I'm taking the absolute value of that ratio. That essentially is saying that we're not concerned about the phase differences between our input and output, because there will be phase differences, and that is a problem with filters. And if you're an audio engineer, you know if you put a lot of filters on some signal, you're really fooling with the phase of that, of all the waves in your signal, and it starts making it sound weird. But we're not worried about that. We're not going to consider the phase of the output. Just looking at the relative amplitudes. Our cutoff frequency happens when the transfer function is equal to 0.707 times the shelf amplitude. So here's the shelf amplitude up here. Normally we would say that would be the input amplitude, but since we have an active filter, we are going to make a gain for our shelf. So this is going to be at some level above, because our gain is going to be greater than 1. It's going to be above our input amplitude. So whatever this is going to be our 0 dB for our active filter. And we're going to see that our cutoff frequency is going to happen when we're at minus 3 dB. And that happens when this term is multiplied by 0.707. Well, we put in an infinite frequency for the frequency in this term right here, and we'll get what the amplitude of our shelf is. That's what this is. And then we're going to multiply that by 1 over the square root of 2 to find this point, which is the cutoff frequency. Now, I shouldn't have said that. That's the amplitude of the cutoff frequency. But the cutoff frequency is here. Okay, so there we are. Just carrying that 2 through. And then, okay, so then this is going to happen when this will be the square root of 2 over our R1 is when this term right here is equal to R1. You see that? So then I just set R1 equal to this, and that I'm going to solve for the cutoff frequency, and there it is. So now we have an equation. We went through all that business with all the math just to get this equation for the cutoff frequency of our high-pass filter. Well, let's hook up our high-pass filter. We do it just like we hooked up the 741 op amp. We start by putting the negative rail to here, the positive rail to here, pin 7. The outputs of the 356 are the same as the 741. We're using a 356 this lab because it has a higher bandwidth than the 741, and we don't want to have the bandwidth of our op amp figuring into our measurements. Don't forget to put all the grounds on your ground tree, and we're going to connect the black wire to the ground rail, which is connected to the ground tree, so that the positive input is connected to ground. And before we start making measurements with our high-pass filter, we're going to just look at the bandwidth of our 356 op amp to make sure that we're going to be operating in a range well below the bandwidth of this thing, the high range of our bandwidth. So we're going to turn up. No, what am I doing? Adjust the input amplitude to 0.4 volts. So that's what I chose to do. So that's at this is at 0.2 volts per division, so there's 2 divisions. And then I'm looking at the output, and I've got a gain of 10, so that means that the output should be 4 volts, and there it is, 4 volts at 366 hertz, and if I'd gone lower, it would have still been 4 volts all the way down to 0. So that now I've increased it to 3,744 hertz. We're still at 4 volts. Still at 4 volts at 37,000 hertz. Still at 4 volts at 124,000 hertz. And we're starting to sag there at 300,000. No, what is that? 300,000. This is there. And so now we're at 549,000 hertz, and you can see our amplitude is way down. Oh, we're at the minus 3 dB point, so that is 3 decibels. We're multiplying the 0.707 times 4 to get 2.8 divisions and it's at 1 volt for our output. So there we are at our cutoff frequency of the op amp itself, even without any kind of filter. So it's acting as a filter for very high frequencies. So we know that if we're below 100,000 hertz, we are safe, because we're way up here at 549,000 hertz is our cutoff frequency. Okay, and that will depend on your gain. So if you have a different gain in your lab, you'll have a slightly different cutoff frequency of your 356. Well, let's add C1 to the circuit. And now we have this situation right here, and we've got our high-pass filter. And note that I've got the capacitor in front of the resistor, but the order doesn't matter. Okay, we're going to make a bold plot using log linear paper, and we'll calculate the amplitude here, our transfer function in dB, by using the equation 20 times the log of the ratio of the output over the input amplitudes. And you know that from your Physics 161 course probably. Or maybe it was through 263. Okay, but you should have known that. Okay, plotting data points starting high from low. So we're going to start at a high frequency, and we're going to go down and see where we get that cutoff. So I've started out at 124,000 hertz, and I'm at 0 dB. I'm measuring 4 volts out, and that's what I expect because I had 0.4 volts in. So I got 0 dB. Okay. Measured the frequency of 37,000 hertz. That's kilohertz. So we're at 37. The way this works is this is 10,000, 20,000, 30,000. That'd be 40,000 right there. So this is 37,000 is somewhere about right there. Okay. And we're still at 0 dB because I've still got 4 volts coming out. Here we still got 4 volts coming out of our output, but now we're down to 838 hertz. So now we're at, see, this is 100 hertz here, 200, 400, 600, there's 800 right up there. We're just a little bit above that, 838 hertz. We have to estimate a little bit, and we're still at 0 dB, so we're still plotting our point at 0 dB. Down to 366 hertz, still at 4 volts. So let's see, 2, 366, no, there's 366 is about there. So we're still at 0 dB at 366. 185. Looks like it's still at 4 volts. So we're still at 0 dB at 185 hertz. So that was 100 hertz. So I have to just estimate between 100 and 200 hertz here, and I put it about there. Now we see our amplitude is starting to go down, and I measured 3.2. I blew that up in my computer to measure it more precisely, and I got, so if I put 3.2 in for V in over V out, that really is not V in, it's the amplified V in with the gain of the op amp. And we get minus 1.9, so there's minus 1.9 decibels for 55 hertz. There it is, 55 hertz. Then I'm trying to get to 3 dB. The 3 dB point is, and you're going to have that trouble, is it's hard because we can't measure really precisely on an oscilloscope. So I calculated that I should get 2.8 volts, but it ends up to be 3.1 decibels, so it's a little bit above our 3 dB cut. And that happened at, it's supposed to happen at 50 hertz, and look at this, it's 32 hertz. Yeah, so I plotted it at 32, so 20, this was 10, so that's 20, 32 was right there, so I plotted at 32. We're a little bit off on that one. Okay, so then when I go down to 22 hertz, I'm at 2.1 volts, and that is minus 5.6 dB, so I plotted that right there. And then I'm down to 15 hertz, I get that was about 1 division here, 1 volt over 4, so it gets me minus 12 decibels at 15 hertz. So we're dropping. I should have taken more points, but it's getting hard when you're at such low frequencies. Now, so I've created my Bode, this is my Bode plot. Now I can extrapolate these two regions, and this is called the shelf. This is a shelf filter, and where those two extrapolated lines meet, that should happen right at your cutoff frequency. I really should have taken another point here to get a better line. Okay, low pass filter. Now we're going to get rid of the capacitor on the input and put it over here. Let's analyze this. I'm going to go through this really fast because I know you've done this in class and it's kind of complicated and it would take up a lot of time. We're already at 18 minutes. Okay, so the current through here is going to be split into these two paths. So there's the current is equal to the current through the resistor and the current through the capacitor. Doing a little bit of algebra, solving for the transfer function. All we're interested is the magnitude of the transfer function. Since these two terms are vectors, oh, look at this. I'm using complex notation. You know how to do that with phasors. So there I just multiplied top and bottom by RF. And now taking the magnitude, we get the magnitude of the transfer function is this. Now this is going to be 1 over the square root of 2 when this term right here is equal to 1. See that? So that's when this is equal to 1, then we have 1 plus 1, and we get 1 over the square root of 2. So we did all that work, and you can go through it slowly if you'd like, to find out that the cutoff frequency equation is the same equation that we use for the low-pass filter. No, for the high-pass filter. Isn't that funny? Okay, we quickly turn our high-pass filter into a low-pass filter by taking out the capacitor on the input. So we're going to get rid of this capacitor here and put the capacitor over the feedback portion of our op amp. and we've got a low-pass filter. Now we're going to go from low to high to plot our Bode plot. So at a low frequency, remember, what is this, 25 hertz, that is much, we had a lot of attenuation with our high-pass filter, but now we have no attenuation with the low-pass filter. Do it again for 70 hertz, we're again at 0 dB, 400 hertz, we're at, I plotted that a little bit off there, didn't I? Because this is 300, so this is 400. It should be above that, but it doesn't matter because it's 0 dB anyway. Now we're getting a little bit of cut at 2,306 hertz, and I measured this to be 3.7 over 4, so it's minus 0.7 dB. So there I am at 0.7 dB at 2,300 hertz. Now we're at 4,246 hertz, and I'm at minus 2.2 dB after I measure the amplitude. And then there's my 2.8, and that's where I'm getting my minus 3 dB cut. And again, this is 3.1 dB. It's not quite perfect because of the inaccuracies of measuring on an oscilloscope. Okay, I'm increased to, this is kilohertz. You can't see the dot here, but that's 11,000 hertz, 203. So there's 10,000, 11,000 would be somewhere in there at negative 7.4 decibels. 23,000, there's 2,000, there's 10, this is 10,000, 20,000 is here, so 23,000 I'm estimating is about there, and we're at negative 13 decibels. And now I have 3 points above the cutoff frequency like I'm supposed to have, and I've got, this is 0.5 volts out, so when I put that over 4, I got negative 18 decibel cut at a frequency of 42,000. So there's 40,000, there's 42,000 is right where I plotted it. Now if I extrapolate this, and I extrapolate that they should be intersecting above, well, I did it better here. They should intersect right above the cutoff frequency, and it's pretty good for the low-pass filter because I calculated 5,005 hertz, and you can see that we got about 5,000 hertz for, there it is, 5,000 hertz, right on the money there. Bandpass filter. What does a bandpass filter do? It's a combination of a high-pass filter over here and a low-pass filter over here using the same op-amp. Will the transfer function be the same as the combined transfer functions of the two high-pass filter and low-pass filter together? You'll find out. Well, we hope you've enjoyed the show.